James, who normally does the intros and everything. Hello, everyone. We have Justin, who's here to talk about a new paradigm within lookups and potentially ZKVMs. Very excited for this. Leaving it over to you.
Cool. Yeah, thanks for having me. I don't really know what I've been to one of these sessions before, and I think it was but did I give a little spiel and then it was a Q&A? I guess I could do that now, although it's all off the cuff. Yeah, I'll just share sort of my views on Lasso and Jolt in a few minutes, and then I guess if anyone wants to ask questions, please do so. So I would say Lasso is a new lookup argument. Jolt is a new paradigm for ZKVM design that builds on top of Lasso and sort of leverages some of its unique capabilities. So let me say a little bit more about Lasso and what I think is new about it and what I think is not so new about it. There is a bunch of it that's not so new. So there are a few variants of Lasso, all presented in the paper, which we can probably improve the presentation of the different variants and how they compare, because we've been getting a lot of questions on them. But the simplest variant, in my head, I call it basic Lasso. We don't use that term in the paper, but there's a parameter C, and this is just C equals 1. Okay, and in basic Lasso, the cost profile for the prover is the following. So to do m lookups into a table of size n, and let's say these are index lookups, meaning you're doing lookups into specific entries of the table. So we sort of define these two analogs. One is unindexed lookups, which is really like set membership, like is everything being looked up somewhere in the table, and then there's index lookups, which is like just like a reading into a read once memory. Read only memory. So the table's like a read only memory, and you're like kind of querying entries of the specific entries of the memory. So in the index case, where the values being, or let me say the indices being looked up and the claimed values, living in those indices are already committed. So we kind of don't charge to commit to those values as part of the problem statement. The prover's committed to these indices and committed to these values, and just proving that, for each index, the associated value is actually the value that resides in that index of the table. The prover commits to m plus n field elements, okay, and they're all small. Okay, so that's sort of the simplest variant of Lasso, and that's its costs. Okay, so just again to summarize, so m lookups, table of size n, the prover commits to m plus n field elements, and they're all small. Okay, to elaborate just a little bit more, they're actually all counts. And so that gives you like more efficiency in certain regimes, right? So like the very first time any table cell is accessed, the count will be 0. Okay, so and committing to zeros is like free. It's like no group work, because like any group element to the 0 is just 1. You don't actually have to do a group operation to figure that out. So yeah, if you're reading like many different cells, like let's say in the extreme case, every lookup is to a different cell, then actually you don't even really pay. The prover doesn't pay for the first m out of the m plus n counts. Okay. Secondly, if n is bigger than m, right, then at most m of the last n counts are 0. So the prover also doesn't pay, to commit to any of those 0 counts. Okay. So that might suggest that big tables come completely for free, right? Because like if you're only doing m lookups into a table of size n, and then most m of the counts then are non-zero, It might, what I'm saying might make it seem like anything that's never looked up is like just completely free because it has a zero count and it doesn't really cost anything to commit to zero. That's not true. The cost for big tables is then coming in because at the very end of the protocol, there is one evaluation query to a polynomial like derived from the table. Okay. Or sorry, the derived from the count, the committed count vector of length n. Okay. And so if n is really big, if the table is really big, that evaluation query will be, like the dominant cost for the prover. Okay, so to try to summarize all of that, right, the prover is committing to n plus n counts. A lot of those counts might be zero in certain parameter regimes. And the big caveat to, making it sound like there's like just no cost to dealing with gigantic tables is that there is an evaluation proof, where the verifier says, hey, like tell me this committed polynomial evaluated at a certain point. And that polynomial is going to have size n, the size of the table. Okay. Does anyone want to ask any questions about that summary of basic Lasso?
Can n not be like 2 to the 128?
Yeah, so okay. I'll get to like the other variants of Lasso, which are, if you want to deal with a table that's that big, 2 to the size 128 or something, you're not going to want to use basic Lasso exactly because of this evaluation proof issue. So yeah, like I think right now, with MSM-based commitment schemes, like it's this weird thing where you can commit to like a gigantic sparse vector in time, like linear in the sparsity. But if that vector has size 2 to the 128, but almost it has only like a million non-zeros, you can commit to it in time like a million rather than 2 to the 128. But then at the end of the day, the verifier will have, or sorry, the prover will have to do cryptographic work. I think the fastest opening evaluation proofs for these things is maybe like square root cryptographic work. And so yeah, that would be like cryptographic work, like 2 to the 64 or something. And it's just not tenable, not even remotely tenable. Yeah, so in order to handle giant tables like that, there are sort of two more variants in the Lasso paper, depending on how structured the table is. And I think people can mainly forget about one of the two variants because we don't actually have an example yet where we need to use it. It's sort of less efficient, but handles a more general kind of structure. So let me just ignore that for now. So the variant that I think, people should know about is what we just call Lasso, but now with this parameter C greater than 1. And this applies to what we call like decomposable tables, which really just means you can answer sort of one lookup into the big table, the table like you really care about, say of size 2 to the 128, by doing basically like C lookups into much smaller tables. So say if the big table has size n, say 2 to the 128, the small tables, this parameter C is such that the small tables will have size like n to the 1 over C. Okay, so if you set C to be like 6, then you can answer, for a decomposable table, you can answer one lookup into the table size 2 to the 128 with like 6 lookups into, one or more tables of size like 2 to the 22 or something like that, because 128 over 6 is 22. And yeah, the cost for Lasso, for general C applied to decomposable tables is the prover commits to 3 C field elements per lookup. And then there's like a fixed cost independent of the number of lookups of something like table size to the 1 over C. And that's coming in because for each of the small tables, the prover has to like commit to these counts at the end. So it's the same issue, that I talked about for the big table, where there's like some cost that grows with the table size. And the whole point of going to C greater than 1 is exactly to reduce that cost. And so by turning like a lookup into a giant table into several lookups into smaller tables, you only pay that table size cost for the small tables, and it becomes reasonable to pay it because the table is, 2 to the 22 is fine for like an MSM or something, but 2 to the 128 is obviously not fine. Yeah, so
Do you think
that
this is do you think this is like theoretically fixable in future work? I mean, it seems like a one-time cost, which is linear, um, and most of the, I mean, generally you use the tables as sort of virtual tables where you use the MLE instead, right? And that can be quite small. Do you think it's fixable?
So by fixable, you mean just avoiding this like end of the one over C cost?
Yeah, I mean, if there could be similar techniques or based on these, call it future work, which just avoids the final cost.
Yeah. No, I don't. So I'm actually working on some theory results, which are gonna have to be taken, with a grain of salt, but that's attempting to, give evidence that this is inherent, right? So that sort of if you want to do a lookup into a table of size 2 to the 128, um, there's sort of no avoiding this issue that the prover like kind of has to commit to like a 2 to the 128 counts, of which most of them might be zero. Like that is the key issue for applying like basic lasso to giant tables. And so we can prove a lower bound again, like it's an unconditional lower bound, so it's not literally saying like there's no better commitment scheme, right? That we don't have techniques to literally say there's no better commitment scheme, but we can say like any commitment scheme that looks anything like the commitment schemes we have today, this trade-off is inherent, right? So what's happening in Lasso is in order to bring the table size like down from n to n to the 1 over C, you have to commit to like C field elements per lookup. It's actually 3C, and I don't know if that 3 is optimal, but anyway, so I think that sort of trade-off, like to get n to the 1 over C, you need to pay C per lookup. That I think is intrinsic. And again, like I can't unconditionally show that, but I can give some evidence or that show that you need to significantly depart from like anything people are doing today to avoid that. Does that make sense? Does that make some sense?
Yeah, but the 3C commitments, are they small?
Yeah, everything's small.
Yeah.
So in Lasso, the only way anyone will ever have to commit to anything, any big field elements, is if the table itself is just like full of gigantic field elements, and then like you sort of can't avoid it, just because even telling you what are the results of the lookups is committing to big field elements. Yeah, so these 3C field elements per lookup plus n to the 1 over C, extra things that is sort of like a fixed cost independent of the number of lookups. Everything's small. And let's see, did I want to add anything else to that? Yeah, so I will say, and I said this on Twitter recently, I think you could have achieved like very similar things, especially basic lasso. All right, so I think this like notion of decomposable tables is like new and so forth, and I can say more about that. But I think like basic lasso, the whole like committing to n plus n things, and they're all small. I think you actually could have gotten that from firstly, like I would say like that result is like kind of, if you squint hard enough at Spark, which is in Spartan, it's already there. But I think you could have gotten that result from other existing lookup arguments, just by replacing the grand product argument with something based on sum check. And so I think the community has sort of still not fully absorbed the power of sum check to reduce commitment costs for the prover. And people are very frequently just unnecessarily having provers commit to things that the prover just does not need to commit to if you just, use sum check the right way. And not only are the things people are committing to, not only is there more of them being committed than you need, but they're also random field elements. So in a sense, like maybe the biggest contribution of Lasso is just to point out that like you know, the random field elements like only need to arise in the grand product argument. All other parts of these lookup arguments don't need random field elements at all. And you can have a completely sum check based grand product argument that, you know, sum check itself doesn't involve any commitments from the prover. Yeah. So hopefully that's a little bit helpful. Any other questions right now? Okay. Another thing I can add, I'm sort of just like, you know, cherry picking my favorite, like, you know, little conversations from Twitter, trying to like aggregate them in one place here. You know, we've gotten a bunch of comments of the form, like people are already like, you know, snarking things like bitwise end by doing like limb decompositions, you know, and computing a bitwise end on each limb with a lookup and then combining the results, which is exactly what like Lasso with C greater than 1 will do. So it's like sort of two questions, like one, like what's new here, and two, like why would you ever describe this as a lookup into a table size 2 to the 128 instead of just like a limb decomposition, or you know, and I, you know, I have two answers to that. The first one is, okay, so we came up with the notion of decomposable tables by looking at sparse polynomial commitment schemes. And actually, the fastest known algorithm for just evaluating sparse polynomials at a desired evaluation point, especially if they're multilinear anyway, literally works in the way I said. So literally what this algorithm will do is take a table, say of size like 2 to the 128, if you're dealing with like a 128 variate multilinear polynomial. It will consider like conceptually the size 2 to the 128 table, okay, that evaluates every single Lagrange basis polynomial at the desired evaluation point. Right? And there's 2 to the 128 Lagrange basis polynomials, you know, over 128 variables. That table is too big, you know, to do lookups into sort of directly. So what it will do is it will decompose that table because it has tensor product structure into C tables of size, you know, 2 to the 128 over C. It will literally what that corresponds to is breaking the evaluation point into C chunks and evaluating all Lagrange basis polynomials at each chunk, right? And literally it will iterate over the non-zero coefficients of the polynomial, and for each one it will sort of figure out like that Lagrange basis polynomial evaluated at the desired evaluation point by doing one lookup into each subtable. Okay, so this notion of like answering lookup queries into a giant table by decomposing the giant table into a bunch of small tables and doing one lookup into each small table, that is how this algorithm works. Okay, and there's no snark here. It's just the fastest known algorithm for this problem. So that's how we sort of came upon the notion of decomposable tables. And, you know, Spark was sort of already doing this because it is a sparse polynomial commitment scheme. And you know, I guess this view that what Spark is really doing is just the provers proving it ran this algorithm I just sort of sketched for you, like correctly. That's maybe a little bit new here. And, you know, then we started thinking about like Jolt and these decomposable tables and like, what are they good for? And, you know, it was at that point, it's like, you know, we're definitely going to want to view like, you know, something like bitwise end as a giant decomposable table, right? Like we have this view of like giant tables that we're going to decompose. Bitwise end is like just a very simple special case of that now. Okay, so the message here is if I introduce like decomposable tables and tell you like, you know, here's the example to keep in mind, bitwise ends. Okay, I think it's a very natural reaction, which I'm seeing like over and over again on like Twitter and stuff. Like, why would you ever call, you know, bitwise end a decomposable table of size 228? Like, that's just making something way more complicated than it needs to be. What really happened is this is a notion that naturally arises elsewhere. And if you then like try to apply that perspective to something like Jolt, bitwise end, you know, is just something you need to deal with. And it's a, you know, this is just a very special case. So I'd say like, yeah, this notion of decomposable tables arose naturally and does seem to be an unlock, you know, because, you know, Jolt is like a new approach to VM design, hopefully more auditable, hopefully more performative. than what people are doing today. The question that, if people had sort of, if everyone was comfortable with like all Lagrange basis polynomials evaluated at R, right? That would be the example I would give of a decomposable table, and the reaction would not be, oh, this is like unnecessarily complicated. I think that's a very technical table, right? Like, most people off the street like won't know what that table is. So instead, I give the example bitwise end. That lets people maybe understand the notion more easily, but then it feels like unnecessarily complicated and artificial. So hopefully that is a little bit illuminating.
Yeah, I mean, it's how did I put it? It makes me mildly uncomfortable, the idea that the ZKVMs of the future could literally just be, we'll look up the value of what the the computation should take at this point in the computation. Do you think philosophically that this is going to end up being more performant than what I would call more mathy approaches?
Yeah, I think there is a philosophical reason to think that this is the way to do things. So here it is. I think I tried to explain this in my second talk at A16Z, but I probably didn't do a great job. Also, it's like, buried like, multiple hours into the talk sequence. So all right, let me see. Please give feedback on whether this makes sense. Okay. So lookup arguments is sort of an unfortunate term. Okay, what I think a lookup argument is, okay, is just a very efficient snark for incredibly data parallel computation. Okay, so let me try to explain that. So like in Jolt, we think of the lookup tables as storing like the big table as storing like the entire evaluation table of some like instruction on 128 bits or something, right? That perspective is useful. Like, I think, some people would have already been viewing lookup tables as like all evaluations of some function, but it's a lot of people would not have been, I guess. So let's have that view. Okay, so what a lookup argument does is it lets the prover commit to, like a bunch of inputs to that function and the claimed outputs, on each input, right? So let's say, there are 2 to the 128 possible inputs to the function, a lookup argument, an indexed one. Like the prover commits to like 1,000,000 inputs to the function and 1,000,000 claimed outputs, and then proves that, all 1,000,000 claimed outputs are indeed correct. Yeah. So that's just data parallel evaluation of the function. Okay. Now, the costs of Lasso are like there's a fixed cost independent of the number of times you're evaluating the function, which is table size to the 1 over C. Okay. And then there's like a constant cost, like 3 field elements committed per evaluation of F per lookup. Right. And so what's happening here is like this is like amazing costs. It's like only 3 small field elements getting committed per evaluation of F. So long as you're doing enough evaluations of F that like the 3CM, where M is the number of evaluations, dominates the end of the 1 over C. Okay. Now that is like a massive amount of data parallelism, right? Because if the input to F has size L, like the table has size 2 to the L, which means, table size to the 1 over C is like still exponential in L. It's like 2 to the L, to some, 1 to the 1/6 or something, right? So it's like exponential in L to the 1/6, it's still exponential in L. Okay. So in order to say that like, that end of the 1 over C term is like not some like ridiculous giant, bottleneck costs that you just can't afford to pay, you really need to be doing like an exponential number of evaluations of F. Okay, but like, here L, in the Jolt context or whatever, like L is really logarithmic in the runtime of the computer. So exponential and L is okay. Exponential and logarithmic is like linear, right? It's just everything is just sort of scaled differently. So that lookup arguments, all they are snarks for data parallel computation, where you're paying some cost that is sort of exponential in the input size to the function you're evaluating over and over again. But like if you're doing like that much data parallel evaluation of the function, it's reasonable to pay that cost. Okay, now CPU execution, virtual machine execution, that just all that is you've got like 60 primitive instructions, and like you're just evaluating them over and over and over and over again, right? Like you run the machine for 1 billion steps. It's just 1 billion evaluations of, you know, these 60 instructions. So it is data parallel computation, and the amount of data parallelism is exponential. Right. And it's because these primitive instructions operate on only like logarithmically many bits, logarithmic in the runtime of the machine. So exponential in the input size to the primitive instructions is like linear or less in the runtime of the machine, you know, you're proving a statement about. Okay, so in summary, I know this was a lot to follow, but in summary, lookup arguments, like it's kind of a misnomer. They're really just snarks for like, you know, incredibly high amounts of data parallelism, but CPU execution is just incredibly high amounts of data parallelism. So they really are the right tool for CPU execution. So to me, the real question is not like, is this the right way to do ZKVMs? The real question is like, what else is this going to be useful for? Which I'm also happy to talk about because I haven't had it, you know, the papers don't talk about that. I was planning some blog posts that I'm behind on now because there's just been a lot of, you know, there's a lot more discussion than I thought there would be, like on Twitter. I spent a lot of hours on Twitter the last few days and stuff, but anyway, does anyone want to ask any questions, or just let me know if that made sense or made no sense at all, or
I thought that made sense. But I think it takes the vantage point of like you start out with assuming that this is the right perspective to take, you know? Like
uh-huh.
like what matters is we have this entity that is inherently very parallelizable, and then you say, okay, well, the important thing is we need some machinery for that, or we need to use a tool which has the same features.
Yeah. So
So
I
it
guess
makes
what,
sense from that point of view, right?
yeah. So just one quick clarification, which I don't, you know, just because my own language is imprecise about this. So once you have access to like commitment schemes, you know, like parallelism is sort of universal, where like, you know, you can take like a machine that's inherently sequential, commit to like its entire execution trace and just like check, you know, each step of the chase in parallel. So when I say data parallelism, it doesn't literally need to be like parallel. It's really just sort of independent evaluations of some, you know, simple function at many different inputs, where, you know, the inputs can sort of be determined sequentially and only proved parallelly, if you will. Anyway, just clarification there. But yeah, no, I think you're right. Like, you know, I'm introducing like the language of sort of doing the same simple thing over and over and over again. Like, you know, just that's how I'm framing things from the start. On the other hand, I think that's almost a definition of uniform computation. So I don't think my personal view is I'm not actually imposing some sort of limited way of looking at things. It's like, you know, uniform computation means doing the same simple thing an insane number of times, basically. Yeah.
I see there are some questions in the chat. Maybe you want to look
Yeah.
them.
Sounds good. I'm gonna start with the shorter of the two. Just yeah. Even though it was a second, so sorry about that. So other use cases. Yeah. So okay, I'm going to say two things about this. For before I answer the question, I'm going to just mention like how I think of Lasso as like a hammer, which is Lasso lets you like take a field element and sort of do like take its binary representation and do simple operations on the bits of the binary representation, right? Without like decomposing the field element into its individual bits, meaning without like committing to the bit representation. Okay, and there's actually like a theorem buried somewhere in the Lasso paper. It uses generalized Lasso, but that says like, you know, asymptotically speaking, Lasso applies to anything of this form. Like, you know, any like, you know, small circuit applied to the bit representation of a field element, like Lasso gives in principle, like some kind of like speed up over bit decomposition for. And so the reason that's the way to view Lasso is the verifier in Lasso has to evaluate the multilinear extension of the table at some random points. And that multilinear extension is exactly something that like corresponds to interpreting indices into the table as bits and spitting out the associated table entry, right? And so those multilinear extension polynomials are quickly evaluatable by the verifier, sort of if and only if the each table element is like a simple expression of the bits of its index. Okay, so that's why like Lasso should be thought of as sort of a way to do operations on the bit representation of field elements without actually like having the prover commit to the bits individually. Okay, so then the question becomes like, what applications is that sort of thing useful for, where you want to do simple operations on the bits of field elements without sort of unpacking them. Okay, so here's like a slightly non-trivial way of exploiting this. So I think this should be useful for sort of evaluating some like standard hash functions, whether it's, SHA-2 or SHA-3 or maybe AES or something, but on many different inputs. So what's happening is if you just want to do like one evaluation of like AES, there might not be a lot of like data parallelism in there, right? Like it just might not be a complicated, big enough computation, and like, you can't just break it into like, simple pieces that are done, enough times for like Lasso to directly be useful. Okay, but let's say you want to evaluate, AES or SHA or something on at least 64 different inputs. Okay, and it doesn't necessarily have to be like all of AES. I mean, it could be, or all of SHA. It could be like, SHA itself maybe decomposes into like a relatively simple thing done many, many times. In which case you wouldn't need 64 different inputs to SHA. Like maybe, if there's some like little simple thing done 12 times per application to SHA, like, and, you want to evaluate SHA on, what is it, like 6 different inputs? Well, that's enough data parallelism now because you're doing the simple thing like 12 times 6 times. Anyway, and there's something from the computer hardware community called bit slicing. What they'll do is like they'll take a Boolean circuit for something like one of these hash functions. If you wouldn't evaluate it on 64 different inputs, like to take advantage of like, that real machines operate on 64-bit words, what they'll do is like they'll take the first bit of each of the 64 inputs and pack it into one word, and the second bit of each of the 64 inputs and pack it into one word, and so on and so forth. And then they'll take like a Boolean circuit for like one copy of the hash function. And like now each individual like end gate, which like, operates just on like 2 bits, is now like a bitwise end on like, 2 64-bit words, and so now you have exactly the situation that Lasso just applies, right? Because you just turn like this Boolean circuit into a circuit that like evaluates SHA on 64 different inputs, and each gate is now doing bitwise AND, bitwise OR. That's exactly the sort of thing that like Lasso is good at. So that's an example where there's no like virtual machine abstraction or anything, and yet Lasso is still useful. I'm hoping this is sort of the right way to actually prove sort of, parallel again isn't the right word, but Merkle authentication paths built with certain hash functions. So that's maybe the main example I have in mind. But higher level, like you should, these lookup arguments are all about economies of scale. That's sort of what I mean by data parallelism, like doing the same simple function on many different inputs. So you should just be looking for situations where that's what's needed. So, evaluating the same hash function on many different inputs is one example. But, there could be endless others. Does anyone want to ask questions about that, or did
It
that make
seems
sense?
similar. That specific application seems similar to folding schemes, right?
That's an interesting question. So folding schemes are about iterative application of a
Yeah,
relatively simple F.
right. You need the sequential aspect of it.
Yeah, so this I guess you wouldn't. This is more, rather than iterative, this is like for data parallel. And again,
Yeah.
data parallel doesn't literally mean it really just means doing the same simple operations many times. Yeah. Yeah, but I'd say like most of Snark design, like most applications have some kind of repeated structure, and exactly what repeated structure means like varies a little bit. So yeah, folding, you really want this iterative thing. Here you really want just independent applications of the same thing. Um, okay. Okay, so I'll go to the next question, then feel free to, pull me back. Okay, so does it make sense to try to generalize the technique to non-fixed lookup tables? Want to provide a sparse function table as advice? Only the table elements. Okay, I think you do need a complete specification of the lookup table. Otherwise, I guess the verifier just doesn't know like what table is being accessed. So I don't think there's like, if the shortest description of the table is like, here are all the elements in the table, and then like the verifier only accesses these elements of the table, I think like you just don't really have any, I think you could probably just prove like a lower bound. Like there's probably like nothing that interesting you can do. And certainly you don't have like repeated you're not doing the same thing over and over again in any meaningful sense in that case. Now these tables do not have to be determined fixed for all time, like in advance. And in fact, in Jolt, all the tables are fixed in advance. But in like sparse polynomial commitment schemes, actually the tables are literally like all Lagrange basis polynomials evaluated at the requested evaluation point determined by the verifier. So in that case, the table is not known in advance, right? You don't know the table until you know the evaluation point the verifier wants to evaluate the committed polynomial at, which in practice is going to come from like fiat Shamir or something in a snark. So you do not need the tables to be completely fixed in advance. All right. What you need is that they have like a sort of, they're structured, they have a small description. So once I like tell you the evaluation point, for the sparse committed polynomial, then I have told you the entire lookup table or something like that. Now, once another way to sort of look beyond lookup arguments, not just like sort of dynamically determined tables, but is to go for, lookup tables are just read once memories. So you could start asking about read-write memories. And in fact, any ZKVM ultimately needs to deal with the read-write memory. And there's an appendix in the Jolt paper where I discuss exactly this. And basically, I sort of summarize like all, I call it memory checking for read-write memories, and sort of, lookup arguments is just memory checking for read-only memories. And I try to give like a summary of like what's known. And basically the lookup arguments, you can let the table be sort of determined dynamically, but like, basic Lasso is exploiting that it's a read-only table. If the table is read-write, stuff gets more complicated and more expensive. So like in Jolt, in order to actually deal with the memory of the virtual machine, which is read-write, we have to, sort of take basic Lasso and change it in some way. Fortunately, there was already a prior paper that did that. Yeah, okay. So I guess that's my response to that question. Cool. Okay, so next question. What are the next steps for Jolts? What's a good way to get involved? Great. So we want to get it implemented quickly, and Michael and Sam, the engineers I've been working with at A16Z, think we can. And we've sort of been planning the last few days to have a clear path forward. And I think we settled on that now. So we'll be reaching out we've been in touch with some external, people who are interested in contributing to the code base. So we'll be following up with those folks shortly. Where I think right after this, I'm meeting with Michael and Sam. Hopefully we get a clear plan, and then we're following up with everybody. Actually building Jolt is going to be pretty technical in a way that I think there's sort of very, very valuable contributions that can be made that's not sort of directly like, let's take the lookup tables for each, RISC-V instruction and glue them together in like the very technical way. I think there's a ton of work to be done to just make the code base like usable and stuff like that. So anyone who's interested in sort of contributing to sort of any of these aspects, I think that'll be super valuable. And ultimately Michael and Sam will kind of be coordinating most of that. But yeah, and once Jolt is implemented, it's a long game. I mean, there's like endless stuff to do, right? So I think there's lots of optimizations. I think we're going to take like our initial path forward is probably going to be maybe at least 50% like slower than like the performance will not be as fast as possible. We're sort of optimizing for like simplicity of implementation and getting it done as quickly as we can. So there'll be a lot of work that could be done to squeeze more performance out. Things as from as simple as like, optimizing the curve library to much more complicated things like, how are we actually kind of routing lookups to the appropriate subtables. And then you can go forever, right? There's RISC-V is one instruction set. People are really, excited about WASM and the EVM and all sorts of things. So yeah, I think there's going to be endless work to do, and anyone interested in getting involved, I think should be able to find a good way to contribute. Questions, comments?
There's another one in the chat.
Okay, cool. So have you thought at all about where Lasso is most appropriate for certain kinds of computations, but not optimal for other types? And yeah. That's a really good question. So basically, when would you not want to use Lasso? Well, one simple place where you wouldn't want to use Lasso is just like small computations without repeated structure. Lasso is if you don't have a big, some kind of economy of scale and repeated structure, I think Lasso is just not very useful. Now, to be clear, I think Lasso is useful for lookups into small and unstructured tables. Like it doesn't have to be a gigantic structured table. It could be a small unstructured table. You still want to use Lasso, but lookup, if you're doing like two lookups lookup arguments are all about like you pay some kind of cost that depends on the table size that's sort of fixed, and then you amortize that cost over many lookups, right? So if you're only doing like two lookups into a table, you probably would rather be better off not using lookups, just like directly compute the thing. And another thing to look at, by the way, there is something like CQ, where you pay a big cost in terms of the size of the table, but then you don't get this like end of the 1/c like online cost. So like it's pure pre-processing. You fix the table, you do like some very expensive pre-processing of the table, and then forevermore, you only pay like 7 random committed field elements per lookup into the table, right? So like in settings where you do want to do two lookups into a table, like CQ might make sense. It wouldn't make sense if you only use the lookup table once and then like never use it again, right? And but like you could do this very expensive pre-processing of a table, and then like forevermore, anyone who wants to do two lookups into that table is fine. You already paid the so those are settings where you wouldn't want to use Lasso, and other things would make sense. That might be. Yeah, I mean, that might be the primary statement, like, just computations without repeated structure are not, don't really call for a lookup argument, I guess. Yeah. Another sort of higher level comment I can make just about my, personal view of the space is, like sort of the most popular snarks today are basically like Planck and Starks, right? And Planck was tailored for non-uniform computation. So it applies to any circuit. Doesn't matter if how unstructured the circuit is. But it pays like a pretty big price per gate of the circuit. Like the prover sort of commits to something like 7 random field elements per gate in the circuit, and like I don't know, something like 4 more like small field elements or something like that. And then Starks are completely specific to uniform computation. It's like baked into the very definition. Okay. And no, so technically these things are incomparable, right? Like you can have a much smaller circuit if it can have like a completely irregular wiring pattern for some things, or just, you have a computation that doesn't have any repeated structure, and like, you can't, Stark doesn't make any sense at all, and Planck would, right? But like most of what people prove today, not all, most, does have repeated structure. And so, at a very high level, you could think of the move from most of the time people think like, the projects that need tons of performance are moving from Plancks to Starks because of the small fields. That's part of it. Another big part of it is just all these EK-EVM projects are uniform and Starks are targeted at uniform and Planck is not. And they're heavily leveraging, speed ups from the uniformity. Okay, something like Spartan applies both to non-uniform and uniform. And it's just if it's a uniform circuit, you get all these prover benefits, like all sorts of things are free. The prover does not pay cryptographically for the number of constraints, only the number of variables. It doesn't pay cryptographically for the degree of the constraints, only the field work, all sorts of stuff. But if your thing was like small and non-uniform, like it also would apply in that setting. You just need to apply a sparse polynomial commitment scheme to the, like non-uniform constraint matrices or whatever. And so, yeah, in summary, my view is like, even if, so Lasso definitely will not be useful for like small or totally non-uniform computations. Even in that case, I think like the right techniques are not necessarily what people are doing today. I think some check still has a role to play. I think, yeah, I'll stop there. Yeah, hopefully that's useful ramblings.
I have a question about aggregating lasso proofs. Okay, we're using sparse polynomial commitments. I think you can use any PCS with it, but we want to use elliptic curves because there's no cost saving if you're just hashing, like because we're using small field elements committing. So we can assume that we're using some elliptic curve based PCS, right?
So sorry, say that one more time. About the last sentence about small field elements.
I just mean, isn't a big thing here that we commit to small field elements, and that is fast if we use elliptic curves. But if we use a code-based commitment scheme, there's not really any difference because we're just hashing,
Okay, so yeah, I need to think through a little more about the benefits of Lasso and Jolt with non-elliptic curve based commitments. I mean, I still think the prover is committing to fewer field elements than prior works. I think the comparison, to prior works gets, less obvious. So I just quick examples. Cairo commits to 51 field elements per step of the Cairo CPU, right? Jolt commits to what is it? Something like it kept going up as we, worked out details. Somewhere between like 60 and 80, I think 60. Yeah, I think it's 60. For 64-bit like RISC-V, right? So that's about the same number of field elements as Cairo for a vastly more complicated CPU, right? So like even just looking at don't worry about MSMs and small field elements and all that. This is still like, I think, clearly an improvement. You compare to like RISC-V and it gets more, they're committing to 275 or so, baby bear field elements. So, you do have, you sort of now have to normalize for the field being tiny, and it gets trickier. But but I do think I'm like actively talking to other people in this call who are on the call right now about like can we take advantage of small fields more in some check than people are taking advantage, know how to take advantage of today. I think the answer is probably yes. I don't want to make any strong claims right now. I'm working on it. In which case, I think there will be significant advantages even in the small field situation for Lasso and Jolt beyond what I just said for like Cairo is clearly it's committing to the same number of field elements per step of a much simpler CPU situation. Anyway, so
So sorry, specifically within the context of aggregating proofs, then, like this is recursive aggregation with Fry is like, I think you have a blog post where you're not a fan of it, but like it's quite feasible and efficient. I'm wondering, in this case, how you see aggregating multiple Lasso proofs. Can it be done efficiently? How so?
Yeah, great question. I would say I'm not a fan of the recursion. I forget exactly, I've discussed it multiple times. So it's a very powerful technique. And I actually think so I just clarify it's I'm not a fan, but I do think there are, just other approaches to designing snarks that make sense if you're looking at different techniques maybe. So anyway, so my view is, and potentially this is the end game, potentially. I'm not like totally convinced of this, but it could. So Lasso and Jolt are all about economies of scale, right? So I think the right thing to do is to break a big computation up into sort of the biggest pieces you can handle, where the bottleneck should be like the limiting factor is like prover space, because the prover is going to have to like do an MSM that's like as big as the piece or something, right? That gives you lets you maximally take advantage of the economies of scale, meaning the speed ups like the Pippinger speed up and the amortizing the fixed cost of the lookup argument over more lookups. So you get the fastest possible prover per piece. But then since you don't have like infinite prover space, you can't have one piece that's like size 2 to the 50 or something. And so then to like connect the different pieces, then you should do some either folding or recursive aggregation. And there will be some details to work out in terms of, I think the fastest polynomial commitment schemes for the prover today have like square root costs, whether it's something like breakdown or the Haro or Hyrax. So you do want to make sure that taking the verifier of those polynomial commitment schemes and turning it into a circuit in order to do proof aggregation or folding or something is reasonable. But I think square roots should be fine, possibly with a little bit of extra effort and optimizations in there. So high level, that's how I see things going. Is that sort of the kind of answer you were looking to suss out?
Yeah, exactly that. I also assume that it wouldn't make sense to use Lasso to do the aggregation itself, because the computation is comparatively small and the lookup table would be quite big.
Yeah, that's a great question. I think a lot remains to be sort of explored for what's the right like combination of lookups and things like folding schemes or aggregation schemes. In some sense, IVC, folding schemes gives you incrementally verifiable computation. Incremental means like you never do any giant thing all at once. Everything is done in little pieces. And so in some sense, it's like antithetical to economies of scale. Okay. But like, there's always like a middle ground. If your prover has like a gigabyte of space, but not 100 gigabytes of space, like that might be enough to get you a decent economy of scale. And so a lookup argument could be useful. Another thing that's been underappreciated, I think, is just how efficient these elliptic curve based things are when committing like just to small field elements and bits in particular. And so this is actually like very subtle. Trying to compare like Lasso or Jolt to Nova, it's actually pretty complicated to figure out like how big is sort of the prover speed up. So with Nova, for let's say you just don't use any lookup arguments. Every complicated operation is done with a bit decomposition. Okay, so like a 64-bit data type is just decomposed into 64 bits. Okay, now the Nova prover is just going to commit to those bits like over and over, like every time it does a 64-bit decomposition, it commits to 64 bits. That is 64 group operations. It's actually, it's half that because zeros are free, right? So like on average, half of the bits are zeros. It's like 32 group operations. Okay, that's not bad, really. And there are prices that come with just having more committed field elements, like these polynomial evaluation proofs. So like if you blow up, like the number of committed field elements by a factor of, 32, your evaluation proofs might be, I don't know, like significantly more expensive now. But the magic of folding is you only do the evaluation proof at the very end, right? Like, it's that's the whole point. So you almost never pay that price. Okay. So, yeah, this is like, it's pretty hard to compete with bit decompositions if you never pay the price of an opening proof. And that's exactly what Nova does. So yeah, I think there's all sorts of middle grounds. A simple way to look at things, which actually is probably going to be pretty powerful, is to just like, break things into pretty big pieces, apply Lasso Jolt to the big pieces, try to aggregate like with Nova, which is way at the extreme of incremental. But most likely, the best thing to do is to also have the aggregation be, not totally incremental, right? And then you sort of, even the aggregation is taking advantage of some economies of scale anyway. Does that rambling answer add some color?
Yeah. I mean, lots of super cool future work to be done here, huh?
Yeah, I think so. I think it can keep keep some of us busy for a while. I see a question in the chat. Is it possible for CQ to improve the performance of Lasso? So my view here, which, take with a grain of salt, but I think CQ and Lasso are just taking fundamentally orthogonal approaches to the same issue. Okay, so in both, they're both sort of leveraging that you can take a giant vector of length n that's sparse and just directly with an MSM commit to that vector in time, like linear in the sparsity. Okay, and the problem with that is just committing to the vector is not enough, because at the end of the lookup argument of the snark or something, there's an evaluation proof. And that does have costs that grow with the size of the vector and not the sparsity. Okay, the way Lasso deals with that is by turning, the big table of size n into subtables of size n to the 1 over c, and sort of never committing to a giant sparse vector, sort of just only committing to like the dense representation of the sparse vector, like the list of non-zeros. So there's never this giant ambient vector that just is mostly zeros. What CQ does is it does literally commit to the giant sparse vector exactly how I said. Okay, and then the way it deals with like the expensive evaluation proof is by finding like a really, really clever way that I myself haven't fully internalized to push all the hard work that's linear for the opening proof, linear in the vector size, to pre-processing. Okay, so they just feel like they're both dealing with the same issue. They deal with it in like literally like opposite ways in my head. And I'm not okay, well, let me think for a second. Okay, I take it back. Because they're orthogonal, you actually could maybe combine them in a potentially interesting way, which is like Lasso, breaks big table into subtables. Okay, we're sort of imagining like making the subtable so small that like every entry of the subtable is red, and so it doesn't make sense to like aim for like costs like linear in the size of the subtable. But CQ is all about pushing costs that are linear in the size of the table to pre-processing, and then online paying costs linear in the size of the subtable. So you actually could literally just do the following, like this is a formal description of a protocol, like apply Lasso but replace the subtable lookup argument with CQ. Right? I think as long as your table is like known completely in advance, like fixed, the subtables are known in advance, I think that would work. Like and if you're not doing all that many lookups into some of these subtables, like that could save you, that could be savings potentially. So that is another thing to explore, which I hadn't really considered. So